So we've started this active calculation of statistical thermodynamics, where we take the quantum systems and calculate USAG plus K. So USAG is the internal energy is U, entropy, enthalpy, Helmholtz energy, Gibbs energy, and the equilibrium constant. And so today we're just going to do the first three, U, S, and H, and then next time we'll do 8 and G and K. Okay, so we'll jump in. So again, this is just the Boltzmann distribution is the I guess the root of the tree. I mean, it is the basis of thermal equilibrium. So we first calculate all of those populations based on the Boltzmann distribution. And then once we know that partition function, we can calculate all of these other parameters. Okay. So in this lecture, we're dealing with internal energy, entropy, and enthalpy. So remember that expectation value, if you can count the number of energy levels, which we're going to do one of these types of calculations today, if you can count the energy levels, then you're going to use this calculation for the internal energy. If you're dealing with moles of molecules and sort of an uncountable number of levels like translation or rotation or vibration, you would use the equipartition theorem. So this is a review. I see everybody writing. Are they all have blank spaces, or you just? Okay. All right. And so we're once we have that internal energy, then we can calculate entropy from the internal energy. Again, we showed this last time. So we have that internal energy is used there, and Q is used here. And then we start using Q and U and H and all of these subsequent calculations. So we're just going to calculate the top two parameters today a couple of different ways. Now, remember, if we have a molecular system where we're dealing with translation, rotation, and vibration, then we would use the equipartition equations for these U values. This would be a little more difficult to calculate the partition function, because you would have to go into that Gaussian sort of expanded partition function if you're dealing with molecules, to calculate the translational piece of the partition function, the rotational piece, the vibrational piece, and remember that long calculation with all the rotational temperatures and the thermal wavelength and everything. And so the calculation we're doing today is quite a bit easier than that. We're just doing the one with countable energy levels. We're using this equation today. And so here's an example calculation. This is one of the most confusing ways I've ever seen this problem's given. And so I kept it in the notes so that I can explain it to you. Okay. Most of the time in a 2 or 3 level system, your energy spacings are given in joules. Many times they're given in wave numbers. This time they're given in Kelvin. Okay. So they're just saying, well, we're just going to say the value of KT at several temperatures. So listen to the text of the problem. And so when I read this problem, I was like, okay, I understand what's going on, but I don't think my students would. And so this is a problem from the book. I don't remember which number, but it says, consider a system of particles having 3 non-degenerate energy levels. So you right there immediately could calculate, or at least draw your diagram, 3 non-degenerate levels. So you would draw your 3 levels. And then it says separated by an energy that is equal to the value of KT at 25 Kelvin. So you could go ahead and put in a K value, multiply that, and get an energy. And so you could label your energy levels with joules, okay? Or you could just leave it in temperature. So that's what I've chosen to do, is leave it in temperature. So again, separated by an energy that's equivalent to KT at 25 Kelvin. So this is essentially K times 0 Kelvin, K times 25 Kelvin, and K times 50 Kelvin. Now, where did the 50 come from? Separated by, right? So the energy levels are separated by 25 Kelvin each. Okay. And so that's our energy level diagram. So this is really the first step in any of these problems, is like try to figure out what your energy level diagram is, because that's what you're going to use then to calculate your partition function. So once you have the energy level diagram, then you're ready to go. That's why we emphasize those so much in the first semester course, whether it was vibration or particle in a box. We're always drawing that energy level diagram. Even the molecular orbital diagram is an energy level diagram. Where are the energy levels? Energies on the y-axis, all these different quantized states. Now that we know where our quantized states are, we're going to throw Boltzmann's distribution at it and see what populations we have. How is it partitioned among all those states at a given temperature? So then we're given a second temperature to calculate the molecular partition function at 25 Kelvin. So this is a temperature, and now you'll be able to see why I kept these energy levels in temperature, because knowing that I was going to use the Boltzmann distribution, I can multiply those by K, and then when I do e to the minus E over KT, that would be the same as e to the minus K times, say, 50 Kelvin over K times 25 Kelvin. Let me change pen color for a second. I'll show you what I'm doing here. So this 25 Kelvin here is in the denominator of this fraction. That's the temperature you're at, okay? And so that's what made this problem confusing a little bit, is that you have temperatures on top and temperatures on bottom. These temperatures on top came from the energy level diagram. Okay, let's pick a green for that, okay? This Boltzmann's constant times 50 Kelvin is this energy level right here, because the energy levels are on top of that fraction. Can I get you to close the door, please? Dr. Hobbs is really going at it today. All right. So this makes our energy, our Boltzmann factors easy to calculate. We have G is 1 for all of them, okay? So all of the G's are 1, so we don't have any degeneracy up front. Here, this fraction is Boltzmann's constant times 0 Kelvin divided by Boltzmann's constant times 25 Kelvin. You see how the Boltzmann's constants cancel? Okay. See here, I just let the Boltzmann constant cancel, and I just have the energy level value up here divided by the temperature. So this 25 Kelvin goes right here, and that 25 Kelvin on top comes from the energy level diagram. So that bottom number is always our temperature that we're using to calculate, and the top number is always the number from our energy level diagram. So in terms of the exponential factors, it's very easy. E to the minus 0, e to the minus 1, e to the minus 2. So it's pretty simple. And you add all of those up, and you get the partition function of 1.503. So let me just pause here just to let you ask questions, because, again, if you need clarification, now's a good time. Just for fun, let's go ahead and take Boltzmann's constant times 25 Kelvin. So what is this actually? So let's calculate that. So 1.38 times 10 to the minus 23 joules per Kelvin times 25 Kelvin. That's roughly 1.4. So that'd be 35, let's see, 3, yeah, 30, yeah, 3, to the negative 22 joules. Okay, so like I said, we could label our energy levels. Like this one would be 3.4 times 10 to the negative 22 joules. The next one would be twice that, so 6.8 times 10 to the negative 22 joules. And this would work as well. And so then in our problems, we would have this one over here be 3.4 times 10 to the negative 22 joules divided by K times 25 Kelvin, which is 3.4 4 times 10 to the negative 22 joules. So and so it'd still end up being e to the minus 1. But we would have done a whole lot of conversions. Necessarily, if you want to be clear, fine. Unnecessarily, if you can figure it out with just the temperatures. Okay, so anyway, I just wanted to show you how unnecessarily confusing some of these problems can be. All right, so now we have the partition function. So let's calculate our internal energy. So same kind of problem. I mean, it's the same problem. We're just extending it. So the system has 3 non-degenerate energy levels separated by an energy that's equal to the value of KT at 25 Kelvin. So that's enough to get our energy level calculation. We calculated the partition function, and now the thing that they want is the molar internal energy. So that word molar is really important. So it's telling us it wants energy. Energy is in joules, okay, but it wants it per mole. So the molar energy in joules. So now this thing in front, so the energy here at 0 temperature, let's look at the 25K again. So instead of using, well, let me back up. Remember how we get this internal energy. It's the expectation value. So it's the energy times the probability. So all of these are the probabilities. And so whenever we're wanting to calculate the molar internal energy, let's look at this energy state E2. Instead of calculating that K times 25 Kelvin, K is in joules per Kelvin units, right? And that's going to cancel this Kelvin and give us joules. But that's not joules per mole. So then I could multiply this by Avogadro's number and get joules per mole. If you take Boltzmann's constant times Avogadro's number, look what you get. So you have 1.38 times 10 to the negative 23 joules per Kelvin times 6.022 times 10 to the 23rd per mole. And so you could get your calculator out, but I'll tell you what it ends up being, 8.314 joules per mole Kelvin. You recognize that? So all this time you've been using the gas constant R, you've just been using Boltzmann's constant in different units. That's the molar value for the Boltzmann constant. So instead of doing all of that K times this, just multiply these temperatures by R. So that R right there. And that'll get us our molar energies. So we have an energy level at 25 Kelvin. What is that in joules per mole? Multiply by R, and you get it in joules per mole. And a level at 50 Kelvin, what is that in joules per mole? Multiply by R, and you get it in joules per mole. So you should get more and more comfortable as we go through the course just picking the constant that gives you the units you want. Okay, if you see a constant that's going to give you joules per mole, then you're totally free to use it. If you see a constant that gives you wave numbers per Kelvin, then you're totally free to use that. You know, the speed of light, instead of meters per second, add a couple of hundred, and now you have centimeters per second. Go for it. Use it for whatever you need, and so that's how these things are done. So you go through here, and you have basically this R, and I did some algebra here. I don't know why. It's trying to confuse you, I guess. The 25 is 50 is 2 times 25, and so I end up with this. I pull the 25 Kelvin out of both, and I have the gas constant here. So that's our simplification of our calculation, and we end up with our average energy of 88.3 joules per mole. Okay. So this is our internal energy. That's going to be, let's just for grins, let's divide that by R. So 88 3 divided by 8.314 joules per mole Kelvin. What am I going to get if I divide that by R? What's the unit I get? Kelvin, okay. So can someone calculate that? What is that? $10? Okay. I'll say 11. 11 Kelvin. Okay. So 11 Kelvin. So that's the average internal energy right here at 11 Kelvin. Okay. And that's interesting. That is the statistical average of the energy we have in the system. Notice how it doesn't correspond to any of the quantized states, but this is the average energy. If we had molecules in a bag, all in this energy, and we pulled out a bunch of them, we would get zero energy. We would like pull them out and listen or whatever we do to determine what their energy is. And then we pull some out, and then we get a few 25s, and only very rarely do we get a 50. And if we take the average of all the experiments that we did, our average value would be 11 Kelvin. Okay. Because that's that thermal distribution. We have a lot of molecules in the ground state. We have a few in the first excited state and very few in the upper state. That's that Boltzmann probabilities that we get for those. Now let's take this information. We have the partition function and the internal energy, and let's calculate the entropy. Okay. So this statistical entropy is described in terms of the number of states that are available at a given temperature. So it sounds very much like the partition function, and in fact, it's just the natural log of the partition function times Boltzmann's constant. So this W, originally that W was called weighting factors. It was sort of related to those probabilities using the Boltzmann distribution, and so so I would just put probabilities in quotes. They're not exact, but they're very similar to the same concept. And I left the W in here not because we're going to start using W instead of the partition function, but that's what's on Boltzmann's tombstone. Okay, so that's pretty cool when you sort of basically come up with the concept of entropy. And the constant you use to convert the log of those weighting factors to entropy is your constant. So that's Boltzmann's constant right there. So that's just a cool tombstone, I think. So that's another picture of him and his signature. So now we can sign our permission slips with Boltzmann's signature there. Okay, so then this bottom equation, really without the constant, is going to be our statistical entropy that we're going to use. And so we have the internal energy, we know the gas constant, we have our partition function, we know the temperature, so we can calculate our statistical entropy for our three-level system. So let's do that now. So again, the same energy level, the same text to set up that energy level diagram. And so we need to calculate the average molar entropy at 25 Kelvin. So we have this internal energy of 88.3. We have the partition function. We have the gas constant. We have the temperature. So we can put all of these factors in here. So this was Q. This was R. This is our internal energy. And this is the temperature of the system. And so we end up with our entropy of 6.92 joules per mole per Kelvin. And notice that the units of that entropy still have the temperature in the denominator. So whereas the internal energy is just joules per mole, but the entropies have that energy per Kelvin. we'll see later why that's useful. All of the other factors that we use the entropy for is we multiply the entropy by the temperature that we're at. And so that per Kelvin goes away, and then we're dealing with energies again. So it's sort of like entropy acts as a scaling factor for temperature. It's how the system changes when you change the temperature. Now, what are some of the definitions that you guys have heard for entropy? Because this is a term that we throw around all the time. There's cartoons that use it. There's a funny cartoon of an office and everything seems to be broken and the windows are cracked and everything is junk all over the floor and the doors open and it says the Department of Entropy. Okay. And everything's all broken and falling apart.
Tendency towards chaos.
Tendency towards chaos. So that's a very similar, very familiar definition. But what is chaos in this system? What? Heat will increase it. Okay, putting heat into the system will increase the entropy. So we know that. It looks kind of strange though. Temperature is in the denominator here. So if we increase the temperature, it looks like the entropy goes down. But the temperature is also in this partition function. And in all the cases that we saw when the partition function was plotted versus temperature, it went up. Okay, and it converged to 1 here. We only had one energy level populated, but as you raised the temperature, it went up. Either it went up linearly, like in a vibrational situation, or to the 5/2 power in translation. So it went up whenever you raise the temperature. So if Q goes up, then you're going to get an entropy that goes up. Okay. So just looking at our energy level diagram, what do we mean by chaos and order? I mean, this is like philosophical, right? This battle between chaos and order that goes, for civilizational times, talking about the battle between chaos and order. What do we mean when we say that entropy is an increase or a tendency towards chaos, mathematically? Because I like to think mathematically, chaos is a slippery word. Right? What does that mean, right?
Oh, randomness.
Yeah. Randomness, yeah. So if I lower the temperature to 0, what happens to my energy level diagram? Is it ordered or random? Yeah, how? What's the order? I mean, I know where the atoms are, or the molecules, or the particles. Where are they? Ground state. That's perfect order. So entropy goes to 0 when you have temperature go to 0. Okay. And so you see this, of course you have in this equation temperature in the denominator, but we're really focused on the partition function. As temperature goes to 0, that Q goes to 1. Okay. And so that's like perfect order. And so as I raise the temperature and Q goes up, I have more options. And so entropy is another way to say it is entropy is an increase in options. Okay. So I have more energy levels to choose from. And so if I have more energy levels to choose from, I have a higher entropy. And I can take away those options by lowering the temperature. So if I lower the temperature, I naturally order the system. If I increase the temperature, I disorder the system. I have more options, and atoms and molecules and electrons can go in any number of different energy levels. And keeping track of them is more difficult. That's why we say it's more random or more chaotic. Okay, so we've calculated these first two values. Let's go ahead and calculate the enthalpy. So calculate the average molar enthalpy at 25 Kelvin, same energy level diagram. So now we use the internal energy here, and we have the gas constant times temperature. And so that's our H, 296 joules per mole. Let's take I'll let y'all finish writing that one down. Once you have these equations, these calculations aren't that difficult, but there's one after the other. So it's kind of hard if you're doing this on the test to get through it all. So you got to, it can't be your first time to do it. Yeah, that's the other thing too. Yeah, you mess up that partition function, you're really toast because it's everything. Yeah. That's right. Yeah. Okay, so let's do a little top hat here. I've got some questions for you. Okay, good. Okay. Yeah, I like the little hourglass from Windows 95. Okay, so if your energy level diagram is in wave numbers, which constant do you use for K in KT in the Boltzmann distribution function? You know, you have that denominator and the exponent, KT. And so your energy level diagram is in wave numbers. All your energies are in wave numbers. Which constant do you use for K and KT? And this is exactly what you're going to be thinking when you're looking at your note card. I got all these constants here. Which one do I use? And so I figured I'd just go ahead and ask now when it's not high stakes. Okay. So here's the bar chart. Come on. All right, very good, very good. A couple of people bit on the speed of light. Okay, the speed of light was thrown in there completely as a distractor. Yeah, but all these other four might be options, right? And so then let's do another one. If the energy level diagram is in joules per mole, which constant do you use for K in KT in the Boltzmann distribution function? It might be helpful to know, in an exponent for that exponential function that should be unitless. And so whatever the units are in that fraction ought to cancel. So whatever's in the numerator has to cancel with everything in the denominator so that you have a unitless argument. Same with logs. You should have a unitless argument inside a log. So like in the last problem, we had wave numbers in the numerator. So we needed wave numbers per Kelvin in the denominator. And when it's multiplied by temperature, the kelvins cancel. And then you have wave numbers over wave numbers. So in this one, we have joules per mole in the numerator, because that's our energy level diagram. And so K in the denominator, even though you see K in the equation that you have on your note card, since your units are joules per mole in the numerator, you're going to use R in the denominator. Because R is just K times Avogadro's number. So you just use R in the correct units. There's a couple of different forms of R based on the different kinds of units that you need. And so use the R that's joules per mole Kelvin in the denominator times temperature would give you joules per mole in the denominator. And that would cancel with the joules per mole in the numerator. You have a unitless fraction in e to the minus whatever that is. So that's, again, just a little bit of tips and tricks, places where people go wrong in the past. So I'm able to head those mistakes off before you get there. Okay, good job. So let's go back. So now let's see what happens with degeneracy. Okay, so we've got a little bit of time. Let's take this same problem and recalculate these things, but with some degenerate energy levels. Okay, so if we have our energy levels at 0 Kelvin, 25 Kelvin, and 50 Kelvin. Y'all decide. Where do you want the degeneracy? You want it in what? 25? How many levels do you want? 3, okay. We got 3 here. Do we want to do anything with the 50 Kelvin? 2, okay. It'd be a really weird one. So it's got crazy degeneracy in the middle and then very little in the top. So yeah, that's all right. We'll see what happens. Okay. So again, we got to calculate our partition function. So and at 25 Kelvin, we're going to calculate Q, U, S, and H. And we have 0 Kelvin, 25 Kelvin, and 50 Kelvin. I'm just going to do it in a table form because I think it's easier to follow. All right, then the degeneracies. Oops, that's a Q. Q and G. I start to write a G and I end up ending it with a Q. So the ground state degeneracy was 1, the 25 was 3, and then a 2 here. We still have that 25 Kelvin and 50 Kelvin, and so at 25 Kelvin, it's e to the minus 0, e to the minus 1, e to the minus 2. Just like if you want to go back and look at the previous slides, you can see what I'm talking about there. So now it's 1 times this, 3 times that, and 2 times that. So let's add up all of those factors. So this one is going to be 1. 3 times e to the minus 1 and 2 times e to the minus 2. And Q is the sum of that column. Can y'all tell me what this one is? Just this little piece. Say again. Okay, and this little piece? 0.27? Okay, and this one was 1.0. Okay. And so our Q is? Okay. So then our probabilities, let's go ahead and calculate those. So this one is 1 over 2.37. This one is 1.1 over 2.37. And this is 0.27 over 2.37. So the first probability is? 42.19. I'll do them fractions for now. 0.42. Okay, and then the next one? 0.46. Yeah, it's bigger because of the degeneracy. And then the last one, I could figure it out maybe, but is it 11? Okay. Okay, 6, 7, 8, 9. We get 0.99. So one of these is rounded. What's that? They all round down? So we got 0.99. Okay. All right, close to 100%. All right, so do you understand what that means? That means we have 11% here. No, 42%. 46% divided by 3 there across all of those, and 11% divided by 2. So that would be our probabilities of being in any one of those levels on average. So then let's calculate our internal energy at 25 Kelvin. Okay, so we have U is equal to R times 0 Kelvin times 0.42 plus R times 25 Kelvin times 0.46 times 0.11. Oh, 50. Sorry, that one should be 50. Oh, no, sorry. Ooh. Wait, is that? Yeah, 50. Yeah, that's right. It's the 0, the 25, and the 50. Those are our energy levels times the probabilities of being each. What did you get? Did anybody have an answer for that one? To calculate this piece, I'll write it down. $95. And this one? Total is 141 joules per mole. Okay, now just we'll work on the others. The others are pretty straightforward, but I really wanted to at least get to this point before we ran out of time. Look what happened. We haven't changed the temperature at all. All we did was add degeneracy. What's our average energy? 141 joules per mole. What was it before? 88. Isn't that crazy? We just added more seats in the upper levels, and now we have more energy. We're at the same temperature, but yet we have more energy. And this is heat capacity. We could put more energy into this system before we went up X amount of degrees. So we're at 25 Kelvin in both situations. But this system has more heat capacity because it could accept 141 joules before it got to 25 Kelvin. The other one could only accept 88 joules before it got to 88 Kelvin. Before it got to 25 Kelvin. Let me say it again. This one could accept 141 joules, and it's only at 25 Kelvin. The other one, it was at 25 Kelvin when it got 88 joules. So it has a smaller bucket in terms of energy per degree. Okay. So again, then this is also going to have a higher entropy. So let's quickly calculate that. So S is equal to U over T plus R then Q. That's a so this fraction, what is that? It's 4 or 5 point something. Do you have the first piece? And the second piece? Yeah. Okay, so the total, we got 12, 12.8 joules per mole Kelvin. Again, we've increased the entropy, and we didn't change the temperature. Just by adding more chaos to the system. We've added 3 degenerate levels, in the second level, 2 in the upper, and there's more options. Again, entropy goes up if you have more options, even at the same temperature. This is why gases expand into empty containers and everything, because, again, think of the particle in a box. If I increase the size of the container, my energy levels drop down. I can populate more of them. So I have gas. You always see this in the freshman. You've got gas in one bulb with a valve in the middle and an empty bulb over here. And you open the valve. What does the gas do? It fills both volumes spontaneously. That's entropy driving that. Because the volume is twice as large. So that means the energy levels are closer together, which means I can populate more of them, which means entropy drives that process. In fact, expansion, evaporation, all of those things are highly positive in terms of entropy. And that sort of leaves us with one sort of thing to ponder. If you were to come into class and see an ice cube on the table, you would know that someone was just here before you, right? Why? It would have melted, right? And it would have evaporated eventually, and there would be no trace of it with the given enough time. Okay, so you know that if you see an ice cube sitting there, that something recent put that ice cube there. Okay, that if you have an sort of eternal span of time, there are no more ice cubes, right? If you come into a room and you see ice or something that is at a low entropy state, you know that it's pretty young. Okay, so just leave you with that. Think about things like comets. That's one of the things that sort of led us to say that the universe had a beginning, because there's comets. There are ice balls flying around. Now they're really old, but still, and they're evaporating or sublimating as they go. And so it's kind of interesting. So entropy is a pretty neat topic. So y'all have a great day.